Lena Maricic do her talk.
My name is Lena Maricic from ATA Engineering. I have been with ATA for more than 15 years. And the talk today will be SWOT thermal model correlation. This is a collaborative effort with the Jet Propulsion Laboratory. So first I will introduce the SWOT mission as a satellite complete by JPL and collaboratively work with the France and the Canadian Space Agency. And next I will talk about SWOT payload TVAC tests. After the test, we did a thermal model correlation. I will talk about the methods and results we used, which is the manual methods, can be labor intensive. And then because it's labor intensive and the time consuming, I explored the automated correlation methods and using heats. And I will compare the results with the manual method. And then I will conclude that my presentation. First, the SWOT satellite stands for Surface Water and Ocean Topography Satellite, again, jointly built by JPL CNES. It will survey 90% of the globe, study the Earth, river bodies, and oceans. It will improve the ocean circulation and climate models and help the monitor the globe freshwater management. And ATA has supported JPL SWOT thermal system design, analysis, and tests since June 2015. So it's about 6 years of support. SWOT is expected to launch at the end of this year. Finger crossed. On the right is the SWOT satellite picture. And then a brief summary of the SWOT payload. There were 3 main modules in SWOT. One is Karen, which is in the center of this picture, and it's a K-band radar interferometer and hosts a lot of instruments inside, and that's where the heat can come from, and it will be rejected by radiators through loop heat pipes. And then nadir is on the top, a lot of antennas on top to communicate with Earth. And on the side are deployable antenna assembly, DAA, and then including the IMA, integrated mast assembly, and integrated reflector arrays. This DAA can be deployed when it's on space. So there are 3 major system thermal balance tests were done for Karen, nadir, DAA, and it's done successfully in 2020. Now I'm moving to the TVAC test for 3 of them. First is the nadir model test. It's 7-day test during March 2020, and this is the nadir picture taken after the TVAC test, actually. And it's wrapped with a MLI, as you can see. The nadir test timeline and boundary temperatures are shown on the screen. And then there were 3 major thermal balance conditions we will be correlated to: hot, cold, and survival cold conditions. And then next, it's an 8-day test in July 2020 for DAA, the deployable assembly arrays. They are on the picture on the right, on the left, they are the DAAs and also flight spare hardware of the Karen and nadir being pinned on the 2 towers in the 25 feet TVAC chamber at JPL. This is a picture taken right before the DAA test start. And then at the DAA hinge area, because it's an important component for deploy configuration, There and one test condition with the IR lamps shine on top of the open hinge area of the DAA. So that's just showing the picture. Very hot lamps are turned on and shine on the DAA hinge. So this is the graph showing the DAA test timeline and the boundary conditions. Boundary condition including shroud and support, ground support equipment. There were three major test conditions: open hinge hot, where the IR lamps were used, and then global hot and global cold conditions. So the next is the Karen test. This is a picture on the left is the Karen stowed configuration. I meant stowed is those two wings, the radiators are folded so that we can fit in the chamber. That's exterior picture, and then in the center is the sort of CAD version of this picture. We can see some of the wings, and also we have a heat exchanger to mimic the flight condition to control the heat exchanger temperature. And then there's on the right is what the instrument sits inside of the Karen. There are 4 major pallets and generating quite a lot of heat during operation condition. So some of the pictures are from one of the paper that was done by my co-author Wang, and then he presents the Karen test in detail in his paper in ISIS July 2020. So if you are interested in the details of the test, this is a two-phase thermal test, and because there's leaky pipes, there were many challenges what we encountered during the test. So there's details in this test that in the paper you can refer, look at it later if you are interested. This graph showing the Karen TVAC test timeline and the boundary conditions. It's about 26-day, 26-day tests, and the reason is challenging and also longer duration than other 2 tests is that there's the instrument stability requirements is less than 0.05 C per minute. So the test naturally would be longer to reach that stability. There's also 3 conditions we need to correlate to: hot, cold, and cold survival. So now I will move on to the correlation part of the presentation. ATA has support 3 model correlations. The goal of the correlation, the goals of the correlation are 3 of them. One is temperature difference between sensor model is within ±5 C. Second is total heater duty cycle difference within a module. Between the test and the model is less than 2%. And then third goal is transient temperature change, DT/DT, is larger or faster in model than the test, or conservatively biased. So I want to summarize our correlation results in a few slides. Here is nadir correlation results. Nadir module was correlated to TVAC with 117 sensors per test case. I meant there were 3 major test conditions, so eventually there were more than 300 sensors you need to correlate to. And we ran about 130 simulations. And the nadir module temperature correlation, for the hot case, we have 98% sensor within ±5 C. Cold case, about 97% sensors. Cold survival case, about 85 sensor within ±5 C, which also shown in the table on the right. And all the sensors, except in the survival, are, temperature difference are within 10 C. In terms of heater duty cycle, hot primary case, 0% difference in total duty cycle. Cold case, 0.8%. Cold survival case, 1.6%. So the duty cycle meet our goals perfectly within 2% goal. And then we also correlate the transient cases. For example, the picture on the right are the just two sensors I pull out for demonstration purposes. We verify the model capacitance and correlate to the test transient case, and we can see we have excellent agreement in terms of the profile and magnitude, and even slightly faster temperature change from the model prediction than the test data. So this slide summarizes the DAA test model test correlation results, and the DAA is a larger number of sensors, about 270 sensors per test case. Ran about 150 simulations. For 3 cases, more than 93% sensors are within 5%, within plus minus 5 C. And then for duty cycles, we have open hinge case, the hot case, about 2.2% difference. Global hot case, about 4%. Cold case, about 2.9%. Didn't quite meet the duty cycle correlation goals of 2%, but I will address those things later. And then we verify the model capacitance and correlate to the test transient case as well. So again, picture on the right just show examples of sensors, how they match in terms of profile, temperature differences, and the DT or temperature change over the course of the time. This one is Karen correlation summary. Karen model about 117 sensors. We per test case, and we ran about 193 simulations to correlating this model. For hot and cold case, more than 98% sensor within plus minus 5 C. In cold survival case, which has a lot of heater power turned on, 86% sensor within plus minus 5 C. And then in terms of heater duty cycle, 2%, all cases are within 2% difference. Again, the model capacitance verified correlated to the transient test. It's interesting, doesn't show my test. I need to go back. Somehow in the presentation mode, the text didn't show, so I'm going to come back this. So in terms of method I was using, I just summarized in the 3 slides here. We use statistical method to quantify correlation process. I won't go to the detail, but if you are interested, you can download the presentation and look at them later. And then we start with parameters that are less certain. That's just a sort of common sense method that was using duty cycle, look at duty cycle temperature simultaneously, heat maps as well to understand the heat flow, which will be helpful to look at the whole picture consistently. So what's the thermal balance correlation exit criteria? It's done when correlations meet all the goals, but sometimes can be challenging, in limited time and budget. So each manual correlation took about 2 months effort for those 300 to 500 sensors per test. So if all methods are exhausted, continued correlation results in diminishing returns. So what we do is compare temperature outliers, which you have larger than 5C difference, to the pretest minimum flight prediction margins. So this is just an example. We have temperature DT larger than 5C, and we compare to pretest flight minimum margins. If the flight prediction minimum margin are large, we think the risk is relatively low, even though our correlation delta T is larger than 5C. So, and we also conduct we also look at the temperature errors, the sensors, locations, and in future flight validation verification process, and see if those sensors or location temperatures are acceptable. So those assessments were conducted after thermal model correlation. Because of the manual correlation is intensive, labor intensive, and time consuming, so I explore the automated correlation methods using heats. So importance of the automated correlation, as I just alluded earlier, that it's improving the efficiency and reduce the correlation timeline for this process. I decided to using heat. It's Siemens software. It's a process automation tool, explore design space and finds optimized solution. And it creates process flow combining internal external simulation software. And it's not limited to thermal simulation software like NX. It can be structure, fluid, and other things. It automates model rebuilding, remeshing simulation in NX. And if the thermal model correlation to test it is set up correctly in heat, essentially it's an optimization problem. So because our SWOT thermal model are built in NX, so we using heat, and I explore the method only using the nadir TVAC test. Hot case only. Remember, we have 3 test conditions: hot, cold, and survival, but I only use the hot case. One of the reasons is faster to run the simulation without heaters. And just to compare in the manual correlation using NX, it's about for the hot case only about 34 simulations. Maybe it's about roughly a little less than a 1 month effort. Again, in reality, we have 3 cases were correlated simultaneously. In total, it's about 130 simulations. And then while the heat, the automatic correlation method ran about a total of 50 evaluations. It's a 5 to 7 days effort. It's parameter optimization type, and we use the default algorithm called Sherpa, and this is also heat proprietary. Sherpa stands for simultaneous hybrid exploration that is robust, progressive, and adaptive. So it's changing the changing the algorithm simultaneously using different exploration tool each time when this new data come in from the simulation. So now I want to compare the statistical results of the correlation between the heat automatic method and NX manual method. On the picture on the right shows the statistical result. For the manual method, it's about 97% temperature sensor within plus minus 5C, and then using heat, it's about 96% within plus minus 5C temperature differences. Again, just want to mention the HEATS automatic method only correlate the hot case, not the cold and survival case. So it's nearly identical result, but the important part I want to mention is the time saving part for the HEATS. It's about maybe a quarter of the time used for the menu correlation effort. So now I want to compare the correlate design variables between the manual and the automatic methods. Picture on it's about total of 32 different parameters we are trying to correlate to. And then I did see, large differences between the correlation parameters. So those differences come from a few reasons. One of the reasons is manual correlation including 3 cases simultaneously, while the HEATS only consider the hot case. So you changing hot case does not necessarily mean the cold case will be good. So you have to change the parameter to meet the 3 cases simultaneously. And also maybe in some of the parameters, the hot case is insensitive to some of the parameters. We don't know, but it also possible multiple optimized solution exist. And so that's why there's a future work in HEATS that will consider hot, cold, and survival case simultaneously to have better comparison of the design variables. So in conclusion, the SWAT team successfully complete 3 payload system TVAC tests and a model correlation in 2020 to 2021. This presentation summarized the manual thermal water correlation methods and the results, and then we reached excellent agreement between the test and prediction. And ATA explore automated model correlation method using HEATS. Only one hot case was correlated currently. There are future work to do. Which automation tool to use highly depends on which thermal simulation software the model is constructed in. HEATS works with NX currently, but not current work with the thermal desktop. I know one other software, Maricic, does work with thermal desktop. And HEATS uses multiple algorithms simultaneously to explore the design space. And also HEATS can reduce optimization or correlation time from months to weeks. The future work will consider simultaneous correlation, hot, cold cases where both temperature and heater duty cycles will be correlated. So I would like to thank my co-authors at JPL, Luang, Somawarana, Evan Valdez, and Luis C. They are my thermal team at JPL. And also I want to thank JPL for general sponsorship and support for the SWAT mission. Any questions?
Yeah, Lena. Yeah, thank you very much for your talk. It looks like we've got some time for questions here. Looking at the chat, how many of the correlation time was active hours versus being computationally driven?
What I meant here, manual correlation, I said 2 months time, which is not, it's my actual engineering hour time, but also including computation time overnight running. But I don't have good exactly split between this. But day and night, you are just running simulation on and on. Some of the simulation, like cold survival case, can take overnight, 15 hours, something like that. So it's very time consuming. So we try to run those cases, transient cases, overnight. So we have results next day, look at the data, continue tune the parameter, run again, just days and actually 5, 6 different computers could be running simultaneously.
Yeah, so it's difficult to get a final figure on it, especially if you're, running different computers in parallel and
Yeah,
things like
that's
that.
right. But I say, yeah, 2 months effort is like nonstop, no
Yeah.
matter, engineering hours or except the sleep time. But, computer running day and night.
Yeah, those engineers need to sleep, but computer doesn't. Yeah, okay. Next question here. You mentioned heats can reduce correlation time from months to weeks. Is this comparing heats to thermal desktop?
Did you ask whether this applies to thermal desktop? Right now, heat does not work directly with thermal desktop unless you develop an interface between heat and thermal desktop. So I don't know, but personally, I have used another software called Veritrack that works directly um, with thermal desktop that also reduce probably your correlation time from months to weeks if you set up correctly.
Okay. Yeah, I think the question was along the lines of, is thermal desktop your baseline for that, I guess the month-long estimate of calculation, and then heat would be, weeks compared to the months with thermal desktop.
It is, I should say heat compared to NX, that makes sense, NX menu. But heat do use NX for simulation. The key is the heat can run the NX simulation without stop. It will sort of using machine learning techniques or algorithms to figure out what's next parameter to tune, as opposed to manually you are running NX simulations. It takes engineering hours to decipher what parameter to tune, how much to tune it. But he's sort of automate that process. But NX simulation time on each simulation, it still takes maybe 8 hours, 4 hours, whatever it is. But he's overall automate this engineering thinking process for you. So in that sense, heat does reduce overall time from months to weeks. That I ran 50 simulation in heat's about a week effort, 5 days actually, and then say set up 2 days. And then the NX 50 simulation, but between each simulation, you have menu process to tune the parameters. That takes time. So heat takes the thinking process for you if you set up smartly, correctly.
Okay, I think that makes sense. Yeah, it reduces a lot of the more or less overhead or the management that you would need with manually inputting it, and you need to kind of babysit it in between runs. Whereas he's just you can set it and forget it, go on vacation, do whatever, take a long weekend and come back and it's ready to go.
Yeah, I do think we do need, even use heat, you need engineering judgment. What is the parameter range to use? What is the common sense? Sometimes, engineering judgment do come in if there were some, results is a correlate design parameter or results do not make sense. And so you still need to set up with common sense or engineering judgment.